Section 16.9 Acid-Base Properties of Salt Solutions. Even before you began this chapter, you were undoubtedly aware of many substances that are acidic, such as nitric acid, hydrochloric acid, and sulfuric acid, and others that are bases, such as sodium hydroxide and ammonia. However, our recent discussions have indicated that ions can also exhibit acidic or basic properties. For example, we calculated the case of A for ammonium or the case of B for fluoride. The sample exercise is 1617. Such behavior implies that salt solutions can be acidic or basic. Before proceeding with further discussions of acids and bases, let's examine the way that dissolved salts can affect pH. Because nearly all salts are strong electrolytes, we can assume that when salts dissolve in water, that they're completely dissociated. Consequently, the acid-base properties of salt solutions are due to the behavior of their constituent cations and anions. Many ions are able to react with water to generate protons or hydroxides. This type of reaction is called hydrolysis. The pH of an aqueous salt solution can be predicted qualitatively by considering the ions of which the salt is composed. An anion's ability to react with water. In general, an anion, X to the negative, in solution can be considered the conjugate base of an acid. For example, chloride anion is the conjugate base of hydrochloric acid, and acetate anion is the conjugate base of acetic acid. Whether an anion reacts with water to produce hydroxide depends on the strength of the acid to which it is the conjugate. To identify the acid and assess its strength, we can simply add a proton to the anion's formula. So X negative plus a proton H plus gives you HX. If the acid determined in this way is one of the strong acids listed at the beginning of section 16.5, then the anion in question will have negligible tendency to abstract protons from water. Consequently, the anion X negative will not affect the pH of the solution. The presence of chloride ion in an aqueous solution, for example, does not result in the production of any hydroxide and does not affect the pH. Thus, the chloride ion is always a spectator in acid-base chemistry. Conversely, if HX is not one of the 7 strong acids, then it is a weak acid. In this case, the conjugate base, X negative, is a weak base. This anion will therefore react to a small extent with water to produce the weak acid and the hydroxide ions. The hydroxide ion generated in this way increases the pH of the solution, making it basic. Acetic ion, for example, being the conjugate base of a weak acid, reacts with water to produce acetic acid and hydroxide ions, therefore increasing the pH of the solution. Anions that have still ionizable protons, such as HSO3, is amphiprotic. They can either act as acids or bases. Their behavior towards water will be determined by the relative magnitudes of case of A or case of B for the ion, as shown in example exercise 1619. If case of A is greater than case of B, the ion will cause the solution to be acidic. If case of B is greater than case of A, the solution will be basic. A cation's ability to react with water. Polyatomic cations whose formulas contain one or more protons can be considered the conjugate acids of weak bases. Ammonium, for example, is the conjugate acid of a weak base ammonia. Thus, ammonium is a weak acid and will donate a proton to water, producing hydronium ions and thereby lowering the pH. Most metals can also react with water to decrease the pH of aqueous solution. The mechanism by which metal ions produce acidic solutions is described in section 1611. However, ions of alkaline metals and of heavier alkaline earth metals do not react with water and therefore do not affect pH. Note that these exceptions are cations found in strong bases. Combined effect of cation and anion in solution. If an aqueous salt solution contains an anion that does not react with water and a cation that does not react with water, we expect the pH to be neutral. If the solution contains an anion that reacts with water to produce hydroxide and a cation that does not react with water, we expect the pH to be basic. If the solution contains a cation that reacts with water to produce hydronium and an anion that does not react with water, we expect the pH to be acidic. Finally, a solution may contain an anion and a cation, both capable of reacting with water. In this case, both hydroxide and hydronium will be produced. Whether the solution is basic, neutral, or acidic will depend upon the relative abilities of the ions to react with water. To summarize, 1. An anion that's a conjugate base of a strong acid, for example, bromide ion, will not affect the pH of a solution. It will be a spectator ion in an acid-base chemistry. 2. An anion that is the conjugate base of a weak acid, for example, cyanide, will cause an increase in pH. 3. A cation that's a conjugate acid of a weak base, for example, CH3NH3+, will cause a decrease in pH. 4. The cations in group 1A and heavier members of group 2B, calcium, strontium, barium, will not affect the pH. These are cations with strong Arrhenius bases. They will be spectator ions in acid-base chemistry. 5. Other metals will cause a decrease in pH. 6. When a solution contains both the conjugate base of a weak acid and the conjugate acid of a weak base, the ion with a larger equilibrium constant, Ka or Kb, will have the greater influence on pH. Figure 1611 demonstrates the influence of several salts on pH.